In this first example problem involving energy conservation, we are told there is a box that's sliding across the top of a hill. The box will encounter a slope, slide down the slope, pick up some speed. We're asked to find the speed of the box here. And then the box will slide down another slope, pick up some more speed, and eventually encounter a spring. When the box encounters that spring, the spring will compress by some amount and then shoot the box back, and the box will now be traveling to the left. However, we are asked to find what is that maximum compression of the spring just before it begins to push back and push the box to the left. To answer this question, we are going to invoke the idea of energy conservation. Energy conservation is often referred to as total energy initial equals total energy final. When I say total energy initial and total energy final, I am implying that there are two important moments in the problem that I'm considering. The first moment that's important I call the initial moment. The second moment that's important I call the final moment. However, in a problem like this, there are actually three important moments. So initial and final are just labels. If I want, I could have three labels as initial, middle, and final, or time 1, time 2, time 3. I'm going to, however, choose to label the three important moments in this problem A, B, and C. So I'll call the moment when the box is at the top of the hill moment A, the moment when the box is at this intermediate level moment B, and the moment when the spring is at its maximum compression, I'll call that moment C. Again, initial, final are just labels. If you have two important moments, if you have three or more important moments, you might want to change your labeling somehow. When I say total energy of something, I'm talking about the sum of all the different forms of energy in a particular scenario. In this particular problem, we have three forms of energy. We could have the energy of motion, that is kinetic energy. So if the box is moving, it will have some energy given as 1/2 mv squared. I have the box having some height above the ground, and at different moments in time, the box's height above the ground is going to change. That implies there will be a change in potential energy due to gravity. And so the potential energy due to gravity is given as mgy. I also have a spring in this problem, and a spring can store energy. So if a spring is stretched or compressed, that spring will store energy, and the total amount of energy stored by a spring is in the form of potential energy. That's given as 1/2 times the spring constant times the amount of compression or stretch squared. So K in this particular problem is 10,000 or 10 to the 4 newtons per meter. And X is the amount from beyond the equilibrium length that the spring is stretched or compressed. Now, when I write E total, that is basically saying the sum of the kinetic plus the gravitational potential plus the spring potential energy. So E total is going to be equal to the amount of kinetic energy plus the amount of potential energy from gravity plus the amount of potential energy from the spring. When I am working with gravitational potential energy, I need to choose where to set my height of 0. The height of 0 is allowed to be set to anything you want in a problem that's convenient. For this problem in particular, I will choose ground level to be a height of 0. So if I set ground level to be a height of 0, that immediately implies this intermediate height will be at an altitude of 5 meters above ground level. And that immediately suggests the top of the hill is going to be at an altitude of 5 plus 10 or 15 meters above ground level. If I wanted to in the problem, I could choose this intermediate level to be a height of 0. That would imply this top of the hill is 10 meters above 0, and at ground level is going to be at a height of -5 meters. There's no reason I'm not allowed to choose anything I want as long as I'm consistent. However, it's nice to have your lowest level be 0 and everything be a positive height above that. It's just convenient to work with, so that's why I chose this particular convention. Now we said the energy is conserved, so E total at moment A is equal to E total at moment B, and that's equal to E total at moment C. If I find the total energy, the kinetic and the gravitational potential and the spring potential at any one moment, I immediately know the energy at every moment. That energy might change forms. You might speed up and slow down. If you gain some amount of kinetic energy, you have to lose that same amount of energy in other forms. And exactly how you gain or lose energy will depend on the particular details of a problem. So, moment C, moment B, or moment A, is there any of these moments that we could right away calculate the total energy? Let's look at moment C. At moment C, the spring is going to be at its maximum compression. If I know what that maximum compression is, I can get a number for the potential energy due to the spring. Well, I don't know what that maximum compression is, so as of right now, I have no way to calculate the potential energy stored in the spring at moment C. So we are unable to find a numerical value for the total energy at moment C. E total at moment B. Well, at moment B, the box is up here. When the box is up here, we know the height of the box, we know the acceleration due to gravity is 9.8, we know the mass of the box. So at moment B, we can get a numerical value for the potential energy due to gravity. At moment B, well, the spring is not going to be compressed at all, so X will be 0. Okay, we know the potential energy due to the spring, it's going to be 0. However, we do not know the speed of the box at moment B. So we know the potential energy due to the spring at moment B is 0. The gravitational potential energy of the box at this moment will be 2 times 9.8 times 5. We could get a number for that. But if we don't know the speed of the box at moment B, we can't find the total energy at moment B. So that just leaves the total energy at moment A. And I can write the total energy at moment A as the kinetic energy at moment A, 1/2 m speed at A squared, plus the mass of the box times g times the height of the box at moment A, plus 1/2 k times the compression of the spring at moment A squared. When the box is up here, the spring is not going to be compressed at all. So this term is going to be equal to 0. When the box is up here, the height of the box is going to be 15. The speed of the box we're given is 5 meters per second. We also know the mass of the box and g. So I could write the total energy at moment A is going to be equal to 1/2 times 2 times 5 squared plus 2 times 9.8 times 15 plus 0. This term is the kinetic energy of the box at moment A. This term is the potential energy of gravity of the box at moment A. And this term is the spring potential energy at moment A, which is 0 because the spring had no compression at that moment. So we have these 3 forms of energy. We could plug this in a calculator, and I find that at moment A, the box will have 25 joules of kinetic energy, 294 joules of gravitational potential energy, and the spring is going to have 0 joules of spring potential energy. So if I add these numbers together, I find that in total, there are 319 joules of energy in this problem. So we are going to use this now. The total amount of energy in this problem is 319 joules. And this is going to be true at moment A and at moment B and at moment C. So specifically, I could say the total energy at moment B is going to be the kinetic energy at moment B plus the potential energy of gravity at moment B plus the potential energy of the spring at moment B. And all of these numbers have to add up to 319 joules. So this has to be 319. Let's think about what's happening at moment B. At moment B, the spring is uncompressed. The spring has no compression to it, so the spring will hold 0 joules of energy. Specifically, if I want to show that mathematically, that would be like saying the compression of the spring x is equal to 0, and if x is equal to 0, this entire term is going to be equal to 0. For the kinetic energy of the box at moment B, I could write that as 1/2 times the mass of the box, which is 2, times the speed of the box at this moment. We do not know the speed of the box at this moment, so I'm going to write it as VB and 1/2 mv squared. The potential energy of gravity at this moment, I could write that as mgy. The mass of the box is 2, g is 9.8, and the height of the box is now 5. So multiply that by 5, and plus 0, I'm not going to bother writing that. And energy is conserved, so I know that these have to add up to 319. Now I have enough information to find the speed of the box at moment B. I put this number in a calculator and I find the speed of the box at moment B is 14.9 meters per second. So this is the answer to part A of this question. Part B of this question asks us what was the maximum compression of the spring. So to think about that, let's consider what happens when the spring reaches its maximum compression. Just before the spring reaches its maximum compression, this box is going to be moving to the right. So here's the box. It is about to hit the spring, and then the box will hit the spring, and the spring will compress by some amount. So here's the box when the spring is at its maximum compression. Just before the spring reaches its maximum compression, the box is going to be moving to the right. If the spring is not yet at maximum compression, the box is still going to be moving a little bit to the right. Just after the spring reaches its maximum compression, that's like saying the spring is stretching out again, the box will be moving to the left. Between the moment the box moves to the right and the moment the box moves to the left, well, the box is neither moving to the right nor to the left. The box will have a speed of 0. So at maximum compression, we could say the speed of the box is going to be 0. We defined the moment when the spring has its maximum compression as moment C. So just to be consistent, I'll call that VC. So what would the total energy of, or the sum of these three things be at moment C? Well, total energy is always conserved. We found that the total energy in the system is 319 joules, and that's never going to change. So the total energy at moment C is going to be 319 joules. So what is the kinetic energy at moment C? Well, if you're not moving, your kinetic energy is going to be 0. So at this moment, the kinetic energy is going to be 0 because we're not moving. Vc is equal to 0. The potential energy due to gravity at moment C. Well, at moment C, we have a height of 0. So the potential energy due to gravity will also be 0, plus the potential energy of the spring at moment C. At this moment, the spring will have a non-zero compression, and the spring does have a spring constant, so this term is going to be something that is non-zero. And specifically, the potential energy of the spring will be the only type of energy that is non-zero. So I could say 319 is equal to 0 from the kinetic, plus 0 from the gravitational potential, plus 1/2 times the spring constant, which we said is 10 to the 4 or 10,000, times the compression of the spring squared. And if I go through solve this in a calculator, I find x is equal to 0.25, or if I want to, I could say x is equal to 25 centimeters. So when the box reaches the spring, it pushes on the spring, and when the spring reaches its maximum compression, the box will momentarily stop moving. Just before maximum compression, you're moving to the right. Just after maximum compression, you're moving to the left. If you're not moving, your kinetic energy is 0. We decided that this moment is going to be occurring at a height of 0. If you want extra practice, you could try setting 0 to be this middle altitude, or setting 0 to be this top of the hill. If you decide 0 is the top of the hill, then this would be a height of -10. This would be a height of -15. But even still, you will get the exact same final results that we found throughout this problem. And therefore, from energy conservation, if I know the energy at any moment in time in this problem, I know the energy at every moment. I know how energy is going to be distributed among different forms in this problem. The energy is going to be distributed as some combination of kinetic potential, gravity, and potential due to the spring. I know they all have to add up to 319. So once I know the energy at one moment, I know the energy at every moment in this problem, and that makes it solvable.